So when we looked at Hooke's law, we arrived at a graph like this one in the top corner, and that was because we were dealing with metal springs, and metal springs tend to uncoil as they stretch and then coil back up again afterwards. And this was the shape of the graph we got, but not all materials do what metal springs do. Also note that I have just put after the word spring, straight metal wires do exactly the same thing. And that's just for completeness. What we'll be doing is investigating metal wires when we come back after half term, straight ones rather than coiled ones. I just want to give you a couple of contrasting curves for loading and unloading for objects and materials that behave differently to metal springs. So I just want to look at two different ones. One is rubber. And so an example of an object made of rubber might be elastic bands. And I also want to talk about plastic things. So we can have a look at polythene for that. Not all plastics behave in the same way, but polythene is a good example. Okay, so the loading and unloading curves for these materials are subtly different to the one for the metal spring, and you need to know kind of why. So when you load something made of rubber, the first bit of force that you apply doesn't actually extend the object by very much, be it stretch it or squash it. So maybe if you find yourself a rubber band later on and you just loop it across a couple of your fingers and just pull gently, that first little bit of force that you apply, it doesn't really extend the rubber band very much at all. Then all of a sudden, the rubber band suddenly extends hugely by the next force that you apply. And that the rubber band gets longer and longer and longer relatively easily. But then you reach a point, and I'm sure you have played with rubber bands at some point in your life, you reach a point where suddenly it just won't extend anymore. And you've kind of reached a limit. And you know if you pull any harder, that thing is going to snap. And so again, more and more and more and more and more force for very little extension. This graph practically becomes vertical towards the end. And then it's much more difficult for you to measure with your fingers how an unloading curve would look, but it comes back down fairly similarly, but differently to how the metal wire did. Elastic bands, I mean, we call them elastic bands, don't we? Because they're fully elastic. They don't become deformed permanently. They go back to the shape they were. If you want your elastic band to be permanently deformed, you need to break it. So the unloading curve, therefore, comes back down, and it arrives back down in the place that it started. Now, that's interesting, but it becomes more interesting when we ask, well, what is it that's going on? So rubber is made up of lots of long polymers that are all tangled up together in a big chaotic mess. And what happens when you then pull on the ends of this is that you a little bit try to untangle the elastic bands. So, you know, think of it as like an elastic band is a tangle of minute, tiny little elastic bands. You try to untangle these long polymers that are all tangled up around each other. And so the first little bit of force that you put on really just does a little bit of untangling, a little bit, but you're not going to get very far with the untangling. The next little bit of force is where you start to stretch those polymers. And then eventually you get to the point where they're as untangled as they're going to be, and they're as stretched as they're going to be. And the next stage after this is to break the thing. And then when you relax it back down again, the polymers shrink back down, and then they kind of tangle up again and back down the way it came. So you kind of go from that state to kind of a kind of stretched out version of the same tangle of polymers. And what's interesting about rubber is that it does this very well. It doesn't damage or move the polymers while it's doing it, not permanently, which is why it comes back down to the same shape it was before. Another interesting thing about rubber, if you look at this this line as a work done thing, so the area beneath the graph is the work done. So you can see that the area underneath the top curve and the axis, that's the amount of work done that was in order to stretch the thing. And then when the polymers all relaxed and it regained its original shape, the area beneath the second curve is the work done by the material regaining its original shape. So we put force in externally to stretch it, and then it gives us the force back when it unstretches. But notice that the amount of work done stretching the spring, elastic band, sorry, the work done stretching the band and the work done by the band unstretching itself are not the same. And in actual fact, we end up with this difference here. And the area of that shape is the difference in energy between what we put in and what came back out again as work. So imagine that you have got a, I don't know, a kid's toy catapult, and you use your muscles to pull back the little ball that you've put in the catapult, and you stretch the elastic, and then you let it go, and the elastic regains its original shape and catapults the ball out into the world. Well, the amount of work that the catapult does on the ball will be this white area here, whereas the amount of work that you did stretching the thing will be this white area plus the shaded area. So the question is, what happened to the missing energy? And that energy there will heat up the material. So again, if you haven't felt that you have spent enough of your life playing with elastic bands and that you feel that there's an empty, missing out part of your soul because you haven't played with elastic bands enough, then go find yourself an elastic band after the lesson and just keep stretching and shrinking and stretching and shrinking and stretching and shrinking. If you do it for a couple of minutes, you should notice, especially if you get a chunky elastic band, you should notice that the material gets hot. Just that constant flexing warms the material up. And we take advantage of that sometimes. So, you know, the common use of rubber is to absorb kind of bumps in the road. So we use rubber tires, and to be fair, we put air in our rubber tires, so it's not quite the same on bikes and cars. So we want to think about something that has rubber tires that take a lot more impact than that. So the classic example is aeroplane tires. You wouldn't want to fill those with too much air, or if indeed any air, because it'll pop when the plane lands on it. So what we do is we can make those wheels, I don't know if we do use solid rubber, but I know that there's very lots of rubber, very stiff rubber, and when the plane lands and it deforms the wheel, what you don't want is for the wheel to then undeform and throw the plane back up in the air. So we need to dissipate that energy, and so rubber's a good material because it gets hot, and the plane lands and the wheels are very warm afterwards. But that's fine, the rubber doesn't melt and it doesn't break, and that dissipates some of the energy from the landing. Okay, let's turn our attention instead to polythene, which is also a load of long chain polymers all tangled up together, but they behave differently to the ones in the rubber bands. So when we untangle the polymers in the rubber band, we're not very good at it, and they don't particularly untangle. They just move slightly and change length a little bit, but then they just go back to a tangled mess afterwards. What happens with polythene is that, again, same thing, we apply a little bit of force and not a lot happens. And that's because all we're doing is kind of just moving the ends of this apart, and the polymers remain wrapped up in each other. And so all we really do is just take the slack out of these loosely coiled polymers. And so a little bit of force creates a little bit of extension. And then similarly to the elastic band, suddenly the next little bit of force makes a very, very big extension. And this is where we have done this, and we have pulled all of the polymers straight. And again, we get to the point where the polymers cannot become any straighter. And so the curve kicks up at the end, just like the rubber band one, and it won't go any further. And the next thing that'll happen if we apply any more force is that the thing will snap. What the difference is between what we did to the polymers in the polythene compared to the polymers in the rubber is that in the rubber one, we didn't move any of the polymers. We just stretched them a little bit and made them straighter, but they remained tangled up. What's happened with the polythene is that we've done a pretty good job of untangling the polymers, and they have permanently shifted past one another. And they are not the tangled mess that they were before. It's like taking a brush and combing them. We've straightened these polymers out, and they're not going to tangle back up again when we let go of them. So what happens then is they just shrink back down a little bit on their bonds. And so you have a fairly straight line that looks a little bit like a Hooke's law relationship. Not quite, it's not perfect, but it's not bad. It's fairly straight for the unloading curve coming back down again. You might have noticed this with shopping bag handles. You put your shopping in a shopping bag and pick the shopping bag up, and as long as you didn't put too much weight in the shopping bag, the handle stretches slightly as you pick it up, but then when you unload your shopping out of it later, you've still got yourself a shopping bag. But if you put too much in the shopping bag, then the handles tend to stretch, or the bag itself stretches until it snaps. And then when you take your food out again, it doesn't unstretch again. It's permanently stretched after that. Interestingly, about these polymers, they often have a preferred tangled direction. And so when you make plastic bags, you make sure that the maximum tangling is across the width of the bag rather than the length of the bag, so it makes it even harder for it to untangle and stretch. We end up with some permanent deformation, which is why we refer to these as, well, one of the reasons we refer to it using the word plastic, because that's plastic deformation. And this permanent deformation is clearly not a good thing for plastic bags. It's annoying. We end up throwing the bag away. We can't reuse it again. But for other materials where this is the case, we quite like this behavior. So for instance, if we're trying to fashion something out of sheet metal and we want to bend the metal so that it takes the shape of, I don't know, a lamp or a bit of a car bumper or something like that. Most of those are plastic these days, but you know what I mean. We'd quite like it that once we'd finished bending it so that it is the shape we want, when we let go of it, we don't want it to boing back into a flat sheet again. If we've just hammered something into the shape of I don't know, a lampshade or something like that for a desk lamp, then when we stop hitting it, we don't want it to boing back into a flat shape again. So we like that some materials undergo permanent deformation when we flex them. It allows us to fashion them into permanent shapes that we want. So from a manufacturing point of view, we quite like things that do this. Okay. That's all I wanted to cover with you this afternoon. I just wanted you to see the difference between some different shaped loading and unloading curves. Oh, I forgot this one. Just in case any of you go on to do engineering at university, this shape and this energy trapped in the middle, this is a common thing that turns up in different branches of physics and engineering. Hysteresis. You might want to Google hysteresis loop, especially if you're going to go on to do any kind of engineering. This kind of loading, unloading behavior, or thing happening one way, thing undoing in the opposite direction. slightly differently to how it did. Hysteresis loop, Google it. Add to your vocabulary. Okay, what I've just covered today is in the textbook, chapter 6.3. I don't think there is anything in the textbook that I have not just said, so there's not a great deal of need for you to read that double-page spread, but there are a handful of questions at the end of it, so we do have a spare 40 minutes now. I think there are only 4 questions, so I don't think it's going to take you 40 minutes to do 4 questions. So if you rattle them off in a quarter of an hour or so, and then go get yourself a well-deserved half-term break. I think I said to you last lesson, I'm not going to give you anything to do over half-term. If you feel the need to catch up on anything you've missed, and you are feeling happy in yourself to do that, then you go for it. But if you have been limping towards half-term and you just can't wait for 3:30 today, then